Hello, today we're going to derive the Euler's formula using the Taylor series. First, you need to know what a Taylor series are. Taylor series are an infinite sum of polynomials that converges to a function fx, like fx equals e to the x, or sine of x, cosine of x, which are nasty functions. So we need to approximate them using infinite sum of polynomials. So let's get started. On the left-hand side, we have the genuine function we want to approximate. And the right-hand side, we have an infinite sum of polynomials. And a0s, a1, a2, these are just coefficients, just numbers, 0, 1, 2. Just plug them in, and you have an infinite sum of polynomials. To calculate these coefficients, we need to differentiate both hand sides with respect to x. So differentiated f prime x equals a0 becomes 0 plus a1 plus 2a2 because this 2 comes down. And similarly, this 3 comes down and 3a3x squared for plus 4a4x cubed and so on. If you differentiate this with respect to x one more time, you get 0, 0 plus 2a2 plus 3 times 2a3x plus 4 times 3a4x squared, and so on. Why we are doing this? This is because we can just plug in x equals 0 for these three equations, and you get a0 for the from the first equation, because if you plug in f0, x equals 0, these terms, higher terms, goes away, and you're just left with f0 equals a0. And similarly, if you do a plug in x equals 0 for f prime of x, which we calculated here, you get all these terms goes away, and you're just left with a1. So f0 equals a0, f prime of 0 equals a1, f double prime of 0 equals a2 because these higher terms goes away. And similarly, if you differentiate multiple times, you get a3 equals f triple prime 0 over 3 factorial, and a4 is f fourth prime 0 over 4 factorial, and so on. So if you just can calculate what f0, f prime 0, f double prime 0, f triple prime zeros are, you just get the coefficients easily. And for example, like fx equals sine of x, you if you differentiate that with respect to x one time, you get f prime x, which equals cosine of x. You just can easily calculate this using the definition of differentiation. And if double prime of x similarly becomes minus sine of x, and f triple prime of x equals minus cosine of x, and f four prime of x equals sine of x. And if you plug in 0 in each of these places, you just get numbers, right? So the definition of f prime of x and sine prime of x is limit h equals 0, is limit h approaches 0, h over sine of x plus h minus sine of x. This is the genuine definition of the differentiation with respect to x and sine of x. So if you plug in sine x plus h, this formula, which you learn in high school, just basic trigonometry, you plug in this where this place is, you just easily calculate that f prime of x, actually sine prime of x, is actually cosine of x, which we, as I said, it was here. So if you differentiate cosine of x one more time with respect to x, you get minus sine of x, and so on. And if you plug in 0 for each of these functions, you can easily calculate that sine of 0 is 0, and f prime of 0 is cosine of 0, which is 1, f double prime of 0, which is minus sine 0, which is 0, triple prime 0 is minus cosine 0, which is minus 1, and f 4 times 4 prime 0 is just sine of 0 again, which is 0. So we calculated that sine of x, which is its Taylor expansion, is this form here. And if you plug in f0, f prime of 0, f double prime of 0 in these places, you genuinely get the Taylor expansion of sine of x, which is just x minus this term plus this term plus minus this term, and so on. Infinite sum of series, polynomials. So by using the same trick, just differentiating the both hand sides and plugging in 0, you get all the coefficients one by one, a0, a1, a2, a3 here. These coefficients by differentiating multiple times, plugging in 0, and calculating them, you genuinely get the function, the Taylor expansion of all sine of x, cosine of x, and e to the x here in terms of infinite sum of polynomials right here. So now we learned the Taylor expansion of like trigonometry, just nasty functions like e to the z, e to the x. Now we're ready to derive the Euler's formula. So the Euler formula uses the Taylor expansion, but instead of plugging in x as a real number here, x as a real number and a real function of e to the x, we're going to put in z variable, which is a complex variable. That's all there is to it. Just complex variable in places where x was a real number, and we just genuinely get the Taylor expansion, the same Taylor expansion of e to the z as here, because uh, just same e to the z Taylor expansion as e to the x. We just replace x where x is with z, and we just get the Taylor expansion, which equals the e to the z function. I'm not gonna prove that today here because it requires some knowledge of complex analysis, which you need to know about Cauchy-Riemann conditions. Uh, this fz function e to the z actually satisfies the Cauchy-Riemann conditions and is infinitely differentiable many times, and is an analytic function. You can prove that by using the Cauchy-Riemann conditions, but I'm not going to do that here. You just have to believe me that e to the z actually satisfies its Taylor expansion as we derived before. Just same Taylor expansion, just plugging in z where x is. So this is the just a uh, brief explanation of what a complex function is. You have z variable, which is in terms of x plus iy, where x and y are real numbers. So in a complex variable, you have this complex variable. You put it in a complex function, and it spits out another complex variable, which is in terms of u plus iv, where u and v are real numbers in functions of x and y. So like generally you can plug in 1 plus I, and you can plug in this function and it spits out like minus 2 plus 2i, and that's all there is to it. So we're used to like fx equals ex, where x is a real number, like x equals 1. You plug it in here, e to the x function, and it spits out e1, which is another real number. So we used to real functions and real numbers, but anyway, so the Euler's formula uses complex variables. Just plug it in where x is, because I said e to the z is an analytic function which satisfies the Taylor expansion and is infinitely differentiable. So you can plug in z, which is I times x, and x is any real number, and I is root minus 1. And you can plug it in the formula we derived, the Taylor expansion we derived, e to the z equals this function right here, 1 plus z squared over 2 factorial, z cubed over 3 factorial, and z4 over 4 factorial plus dot dot dot, all the sum of polynomials. Where z is, you can plug in ix, just plug it in there in this Taylor series, plus dot dot dot, and you get, if you sort this out, you calculate this, you sort this out, you have e to the x, ix, and all the real numbers, because x is a real number, in front, and if you plus I times all the real numbers with I in it, you factor out I, common factor out, and you get these two terms, which is actually, if you look close enough, we derived the Taylor expansion of sine of x and cosine of x, and this is actually, this first term here is cosine of x, this becomes cosine of x, and this term here becomes sine of x. So you can briefly summarize that e to the ix equals cosine of x plus I sine of x, sine x. And if you plug in x equals pi, because x is any real number, it satisfies x, any real number of x satisfies this function equation. So if you plug in x equals pi, where places x are, you get e to the I pi equals cosine pi plus I sine of pi, which you can calculate sine of pi equals 0, so this term goes away, and this term equals -1, so if you place -1 over the other side of the equation, you get I pi plus 1 equals 0, which this generally is the Euler's identity formula, Euler's formula. This is the Euler's formula, by the way. Euler's formula. This is the Euler's formula, and this is the Euler's identity. Thank you for watching.